On September 17, 2025, a backyard telescope in Austria locked onto a faint blur passing among the stars. Thomas Layman had been monitoring this object for weeks. It was 3I Atlas, the third interstellar comet ever identified, racing through space at nearly 60 kilometers per second. That evening, something extraordinary happened. The comet abruptly flared in a green hue, not gradually, but within minutes. Layman watched as its brightness sharply increased, the glowing haze around its nucleus intensifying, as if someone had turned up a cosmic dimmer switch. When he confirmed his instruments were functioning properly, it became clear the comet itself was undergoing a sudden outburst. A few hours later, seasoned comet photographers Michael Joerger and Gerald Raymond in Namibia aimed their telescopes toward the same target. With decades of experience and having observed countless comets, they were stunned by what appeared in their images. The comet wasn't merely brighter, it was surrounded by an eerie emerald glow, with a visible distortion rippling through its tail like a wave. As promised, an amateur astronomer had captured an interstellar object behaving in a way that defied expectation. Fast, unpredictable, and unlike the slow, steady evolution typical of comets. Could 3I Atlas have shifted internal modes in real time, ejecting massive amounts of gas and dust in one sudden burst? The vivid green hue offered a clue. This color typically results from diatomic carbon, two carbon atoms bound together, glowing green when energized by sunlight. Most comets contain some, but this amount released so abruptly was highly unusual. The twisting motion in the tail hinted that something external had also acted on the comet. Days earlier, the Sun had unleashed a coronal mass ejection, an enormous blast of magnetized plasma traveling millions of kilometers per hour. Forecasters calculated its trajectory to intersect directly with 3I Atlas around September 24th or 25. The timing aligned perfectly, the green flare, the tail's kink, the sudden brightness. Humanity might be witnessing for the first time our sun colliding physically with a visitor from another star, and a backyard telescope caught it unfolding live. So what exactly did the astronomers record? The light curve gives the first piece of evidence. This brightness over time graph didn't show random variation but a smooth, consistent rise, indicating a real physical event. The color change added another layer. The coma grew vividly green, then slowly faded in intensity but did not return to its prior state. 3 independent observers on 2 continents confirmed identical results. Same timing, same hue, same brightness shift, eliminating any chance of technical error. The tail's frames revealed dynamic changes too, bending and rippling, as though some force had moved through it. Once reports spread, both professional and amateur observation networks acted quickly, retrieving data to compare and verify. The consensus was unanimous: it was real. Chemically, the green emission pointed to freshly released diatomic carbon, excited by ultraviolet light from the sun, the same physics that makes neon lamps shine. That meant the comet had suddenly expelled a huge quantity of carbon-based gas. Why it happened then led to 3 main hypotheses. The first, a new vent opened. Comets are irregular, with hardened crusts overlying untouched ice. As they approach the sun, internal heat builds until a weak area splits, exposing fresh ice that sublimates instantly, ejecting gas and dust in a torrent, explaining the green flash and brightness leap. The second, the solar shock wave struck the comet. A coronal mass ejection carries both plasma and magnetic fields. When such a wave hits a comet's atmosphere, it can heat and compress it, even reshape the tail, like wind whipping through a windsock, matching the observed ripple. The third, the nucleus is tumbling unpredictably. Comets often rotate, and if 3I Atlas spins unevenly, certain sides might face the sun periodically, triggering bursts when freshly heated. Each scenario makes its own predictions. A new vent would keep brightness elevated for days or weeks. A solar shock would cause only a brief flare. A tumbling nucleus would show periodic brightening cycles. To distinguish these, astronomers use high-cadence photometry, frequent brightness measurements taken over time, to identify whether the pattern is sustained, fleeting, or repeating. But what makes this observation exceptional is its origin. This is no ordinary solar system comet, but one formed around another star, traveling across interstellar space for countless ages. Now, for the first time, we're watching how such an alien object responds directly to our sun's power. Beyond its beauty, this moment holds scientific weight. Interstellar comets are physical messengers from distant systems. Every gas molecule and dust grain they carry preserves chemical signatures from worlds we may never reach, offering a rare glimpse into the wider galaxy's ancient, unseen chemistry. A faint star barely visible to us, and a planetary disk that took shape billions of years ago set the stage for something remarkable. When 3I Atlas unexpectedly flares, it performs a crucial act. It peels back layers. The ancient outer surface, weathered for eons by cosmic radiation, gets blown away, revealing untouched material beneath that encounters sunlight for the first time. This unaltered matter preserves the original chemistry from the comet's birthplace, allowing astronomers to analyze pristine ice unmodified since its formation. The sudden outburst offers a rare opportunity to probe composition normally hidden from view. Before the flare, 3I Atlas appeared relatively calm, its spectrum showing only certain gases. Afterward, new compounds surfaced with shifting proportions and altered spectral colors. It resembled peeling layers off an onion, except the comet itself conducted the peeling. Timing is essential. Right now, 3I Atlas remains bright enough for tracking by mid-sized telescopes, but in a few weeks it will fade while retreating from the sun. By next year, it will vanish entirely, accelerating back into interstellar space. This is a fleeting window, making every observation count. Amateur astronomers become indispensable during such moments. Large observatories like Hubble or the James Webb Space Telescope work under strict schedules, dedicating only limited hours to each target. Amateur observers with personal telescopes can watch nightly, filling in crucial data gaps. When unpredictable events occur between professional sessions, amateurs capture them. That is exactly what happened here. Without Thomas Layman's backyard telescope, the flare might have gone unseen. But another factor raises the stakes even more: the comet's mass. Before continuing, consider this question. What ignited that sudden spike first? Was it internal pressure cracking a vent open, or the solar shock wave colliding from outside? Share your theory, then keep following, because the prevailing explanation might surprise you. If you appreciate evidence-first analysis where data drives discovery, subscribe for more updates like this as they unfold. Now back to the issue of mass, a truly game-changing detail. When astronomers mapped 3I Atlas's orbit, they found something odd. Its trajectory showed almost no non-gravitational drift. Typically, as comets eject gases, those jets act like tiny thrusters, slightly altering their motion. Over time, that deviation accumulates, moving the comet from the path predicted by gravity alone. Strong jets cause large shifts, weaker ones barely move the comet. In this case, 3I Atlas exhibited virtually zero shift. It followed its gravity-defined course almost perfectly. That clue revealed something profound. Either its jets are impossibly balanced in every direction, canceling out perfectly, or the nucleus is so massive that the jets exert negligible influence, like trying to move a giant cargo ship with a handheld fan. The data lean decisively toward the second explanation. Researchers led by Harvard astrophysicist Avi Loeb performed the calculations. For the outgassing to have so little effect, the nucleus must measure at least 5 kilometers across, potentially more, and carry a mass exceeding 33 billion tons. That's several magnitudes larger than any prior interstellar visitor. Oumuamua was just a few hundred meters long, and Borisov's nucleus was under a kilometer, yet 3I Atlas dwarfs them both. This scale changes everything. A comet that barely shifts under thrust suggests immense density. Its rare explosive flare cannot be from minor surface dust flow. It signals deeper structural stress. Heavier objects conceal internal complexity, layered crusts, hidden reservoirs of volatile ice, and fracture patterns invisible to telescopes. When something so massive brightens 40-fold in a month, the cause must come from below the exterior shell. To put it plainly, if a comet emits gas steadily, its path wobbles. 3I Atlas doesn't wobble, meaning either its jets balance precisely or it's too heavy to budge. So when it does suddenly flare, that's significant. It hints at deeper fractures venting ancient material, untouched since the comet formed around another star billions of years ago. This brings us to a more intriguing notion. Perhaps it wasn't just one trigger. Many discussions separate internal venting and solar shock into competing ideas, but a two-stage process matches the timeline better. Stage 1 begins as the comet heats on its solar approach. Internal pressure builds beneath the crust, and a weak point finally bursts open, venting gas and lighting the green coma. Stage 2 follows when the coronal mass ejection hits, compressing the active coma and twisting the tail into the rippling kink seen by observers. The sequence vent first, shock second accounts for both the bright green surge and the morphological shift in the tail. Amateur astronomers can even help confirm this through polarimetry. When light scatters off fine dust particles, it becomes polarized, and the degree of polarization reveals details about the grain's size and composition. Measuring these changes over time can help verify if the flare was caused by internal venting, solar impact, or a combination of both. You can measure this using affordable filters mounted to your telescope, no million-dollar instruments required. Detecting unusual polarization would indicate that the dust grains are larger or darker than those in typical cometary material, reinforcing the hardened crust hypothesis. Over billions of years, cosmic radiation could have welded the grains together, forming denser, darker particles. When those particles escape during a flare, their behavior in polarized light becomes distinctive. Picture it like this. Sunrise warms a frozen lake, the ice cracks under thermal stress, mist rises, and the wind reshapes that mist into patterns. The crack is the vent, the wind is the solar shock. Both events together explain what observers see. Many viewers asked about the comet's green color. That glow generally points to diatomic carbon fluorescing under sunlight, meaning a green flare reveals fresh gas, not merely scattered dust. That's what makes this footage scientifically essential. It's about chemistry, not just spectacle. We are witnessing molecules forged in another star system interacting with our Sun for the first time in billions of years. And the timing could not be better. Spacecraft near Mars, NASA's Mars Reconnaissance Orbiter and ESA's Trace Gas Orbiter, were scheduled to observe 3I Atlas around October 2nd, just days after the flare, and its close pass by Mars on October 3rd. A secondary vantage point changes everything. Earth provides one viewing angle, Mars orbit another. Together, they reveal the geometry of the comet's jets, the vent positions, and how the tail's kink propagated through space. Solar missions like the Parker Solar Probe and Solar Orbiter can add further context. These spacecraft track coronal mass ejections as they move through the solar wind. If they captured data from the same CME that struck the comet, researchers could synchronize that information with amateur observer timestamps. The exact moment the shockwave reached 3I Atlas would then be measurable, not theoretical. Optical events logged by amateurs, plasma signatures detected by solar probes, and imaging from Mars orbit would collectively confirm the two-stage model, vent activation followed by solar impact. If all timing and trajectories align, coincidence is ruled out and the sequence becomes clear physical cause and effect. This has inspired another leading idea. The nucleus might be a contact binary, two lobes fused together and tumbling end over end. One side could heat faster, causing uneven outgassing that drives periodic brightness surges. Another theory proposes that a carbon dioxide-rich layer opened during the flare. Because CO2 sublimates at lower temperatures than water ice, a pocket exposed to sunlight would erupt violently. That explains both the intense green emission produced by carbon atoms released from CO2 breakdown and the rapid dimming afterward once the pocket empties. Both models make distinct predictions. If the comet is tumbling, we should see periodic flares matching its rotation. If the activity stems from random CO2 pockets, the flares will occur irregularly. A repeating brightness cycle would confirm rotation. Unpredictable flares would favor the pocket hypothesis. Testing this is straightforward. Take brightness measurements every 10 minutes with identical filters over consecutive nights. If flares recur rhythmically, tumbling dominates. If they only follow solar storms, the sun drives them. Amateur setups already possess the required capability. The strength of citizen science is clear. Coordinated observers can maintain round-the-clock coverage by chaining sessions across time zones, eliminating observational gaps. Sharing unprocessed flux measurements instead of only composite images allows data integration from multiple telescopes. Averaging these readings smooths out errors and reveals true variation. Adding polarization data enhances precision. Basic linear polarizers, costing only a few $100s, screw onto most telescopes. By rotating the filter and capturing images at various angles, you calculate polarization percentage. Unified data from a dozen contributors can produce a light curve equivalent to a single telescope operating continuously for weeks. Such collective effort compresses professional scale observation time into days, fueled only by coordination and standardized procedure. Detecting repeating flares would map the comet's internal rotation and active zones. This effectively allows astronomers, professional and amateur alike, to chart an interstellar body's surface from 200 million kilometers away using backyard tools. Many skilled hobbyists already maintain advanced equipment. Their contributions could settle the debate between vent activity and solar shocks. Submit your timestamps and hardware details, and the most precise datasets will be featured in the next analysis. This is a one-time opportunity to contribute genuine science on an object that will never return. Once 3I Atlas exits the solar system, it's gone for good. So what's the current consensus? The strongest fit remains a two-stage sequence: vent activation first, solar shock second. This model explains the timeline of the green flare and the tail's twisted structure while accounting for the comet's stable trajectory despite intense activity, a result of its massive nucleus. Smaller, secondary outbursts should appear as rotation stabilizes, with tail dynamics reacting to future solar gusts. The sun's plasma output never ceases. Each subsequent CME that crosses the comet's orbit can trigger another observable event. Every flare reveals deeper layers, effectively allowing astronomers to perform real-time geological excavation on an ancient interstellar object. This matters far beyond curiosity. Interstellar ices hold clues to planetary formation in other star systems. Every star's protoplanetary disk forms at different temperatures, producing varied chemical compositions and condensation zones. By studying the gases and dust from 3I Atlas, we are sampling the raw materials of another system, learning whether it possessed water, carbon molecules, and complex organics necessary for life. Understanding the comet's outgassing cycles also improves predictions of future outbursts and possible fragmentation events, protecting spacecraft and enabling future mission planning. If a probe ever intercepts an interstellar visitor, these refined trajectory models, built partly on amateur observations, will be its navigation guide. Backyard astronomers today directly influence tomorrow's exploration designs. Their observations refine orbital models, test hypotheses, and verify data. Subscribe for reliable analyses grounded in observation, not speculation. Amid endless online speculation, we focus solely on evidence. For newcomers, here are the essentials. The coma is the glowing gas and dust envelope around the nucleus. The tail, shaped by sunlight and solar wind, splits into a curved dust tail and a straight ion tail. An interstellar comet's hyperbolic orbit, eccentricity above 1, proves it's unbound to the sun, arriving from beyond and destined to depart again. Previous examples include Oumuamua in 2017, small and elongated with odd acceleration, and Borisov in 2019, a classic cometary body. 3I Atlas is the third such interstellar traveler. Survey networks like Atlas and Pan-STARRS continuously scan the sky, spotting objects that shift position between nights. That's how interstellar comets, asteroids, and other transient bodies are found. Green comas trace diatomic carbon bands excited by ultraviolet light, while cyanogen glows violet and sodium glows yellow, each emission revealing its chemical fingerprint. Continued astrometric tracking narrows orbital uncertainty, and factoring in non-gravitational pushes from jets refines predictions. That is why steady, repeated observations are indispensable. At the heart of this story lies a breakthrough captured not by billion-dollar space telescopes, but by enthusiasts under open skies. We are watching an interstellar comet evolve in real time. The two-stage model, vent opening and subsequent solar shock, fits the evidence precisely. More data will refine it, but already the event underscores a truth. Space continues to astonish us, often from a backyard rather than a lab. Thank you to those contributing thoughtful analysis and disciplined skepticism. Both are vital. Stay tuned for verified updates on 3I Atlas as new spectra and Mars-based data arrive. Track the brightness curve. Debate vent versus shock. Use the data, make it testable, and keep expanding what we collectively know.